to report on some work I did with Dipasquale for the student of mine who is in the audience, and Professor Millot is in Paris, maybe approaching slowly this place. Who knows? We will see. Possibly in time for his talk. And okay, we study a variational problem for nematic liquid crystals, and which are kind of rod-like molecules filling a certain container inside the fluid, and essentially to describe this kind of liquid crystal, there are several models. Essentially, the idea in the Onsager theory is to give a probability measure at each point of the container, giving a sort of a local average of the orientation. And these are too complicated descriptions, so better to pass to a finite dimensional one. In the Landaude Gennes theory, essentially one uses the so-called transfer, so 3 by 3 symmetric experiences with 0 trace. It's a kind of second moment of this probability measure. So in a sense, it's a kind of rough description of the Onsager description. And it's even possible to simplify it further instead of using matrices, using a unit vector and a scalar, which vary pointwise. So this is the mean orientation, and this is the so-called degree of orientation. And the system model instead is the Frank-Kozeny model theory, in which you just have the orientation. And the molecule has a symmetry, a two-tailed symmetry, so the actual description is through the projective plane, because the n minus n are indistinguishable. So this is the basic object, this family of matrices, giving at each point of the container the kind of orientation. And what I want to talk about is a variational theory, so there is no dynamic. Static theory, say, at equilibrium for minimal energy configuration. And of course, the dynamics is also very, very interesting, but very, very old. So now the idea is that inside the container, it's better to use another scalar also that you attach to each matrix, described in terms of the normal and a trace of power, so that in a sense you distinguish matrices depending on the behavior of the 3 eigenvalues. So from point to point, you have a matrix, you have these real eigenvalues with 0 sum, and you order increasingly, and essentially you distinguish inside the container points where all the eigenvalues coincide. This is the isotropic phase, or where 2 eigenvalues coincide. Possibly the smallest is the positive uniaxial phase, or the 2 biggest. So you have this uniaxial phase, and essentially for uniaxial matrices, you are back to the Leslie-Erikson description. So the tensor has a special form in which you recognize a vector and a scalar. So uniaxiality means this special form of the matrices. And essentially, the typical matrix is not uniaxial. These 3 are distinct. So it's interesting to single out inside the domain the level set of this biaxiality parameter, which is in a sense a surface inside the container. Okay, so the idea is that for a generic configuration, a family of matrices, you distinguish inside the container where you have isotropic phase, uniaxial phase, or truly biaxial matrix. And so the theory is variational. You have an energy in the spirit of Landau theory of phase transition. So energy with several pieces. Potential energy and the elastic energy. This is the one constant approximation. It's just to model the simplest situation. Of course, one can consider more general elastic energy with different Frank constants, etc. But the kind of qualitative picture I want to present in the next slide refers to this model situation, because many tools are restricted to this model energy, not available in the energy. And so there is this issue of phase transition, which competition within potential energy and elastic energy creates a slowly varying field because of the gradient term that possibly wants to take as small as possible the potential energy. Okay, so there will be some structure at large scale which are due to the potential energy, and in a sense the variation in space is smooth, in a sense, because of this gradient. And the potential energy is quartic in the matrix and depends just on the eigenvalues. So this is the bulk potential with material constants, at least the elastic constants. So the idea is that now for this energy, one normalized to have a negative potential. Yes, the relevant object is the bottom of the potential, is the so-called vacuum manifold, which is essentially the uniaxial matrices and of particular fixed norm. So it's just uniaxial matrices sitting inside a four-dimensional sphere of a certain radius, which depends the radius on the parameter. Okay. So we have this vacuum manifold, which essentially is the real projective plane, as somehow in the talk by Benoit. In that case, it was the real projective line. Here we have one-dimensional mode. And the most important thing is that this vacuum manifold has non-trivial topology here in terms of the first and the second homology group. And because of that, you have topological defects. For technical reason, it's better to rescale slightly the matrices in such a way that the projective plane is really inside the unit sphere. So I'm normalizing the radius. And the natural boundary condition to exploit this topological defect is the so-called homeotropic anchoring. That is at the boundary, at the point of the boundary, you have matrices which are cooked up as a uniaxial matrices given in terms of the outer normal. So you have the outer normal to the point of the domain, and out of that you cook up these uniaxial matrices, which essentially cost zero potential energy. Okay? Because of that, when you minimize the energy inside, you will see topological defect appearing. So of course, the energy is well defined for Sobolev configuration and to integrability for the gradient. And for the rescale potential, what is relevant is that the rescale potential is the sum of two positive non-negative contributions, depending on Q, and with the physical parameter in front, which are respectively the -1/2, the nematic correlation length and the biaxial coherence length. So the idea is in the next slides to play with this parameter to enforce some effect that creates this topological difference.
So the zeros of W are exactly the
is still Turing. Yeah. While for this piece, it's just the unit sphere. Yeah, exactly.
So like this, you will see how when A is small or large, you go to.
Yeah, we are not playing with the low temperature limit that corresponds to playing with just A. Here we are not playing with L. This is for expert with elastic constant that in a sense is enforcing at the same time these two pieces to be small. What we are going next is to play just with this quantity, and so we will see what happens. So in a sense, it's slightly different from the other results in the video. Okay. So indeed, we consider two cases. One is when formally mu is plus infinity. So we still have really the constraint of having a unit norm tensor. So the energy is still of the same form, but because of the unit norm constraint, when you write the Euler-Lagrange equation, you have a term, a nonlinear quadratic term in the gradient accounting for this constraint. And the other situation we consider is where mu is large, so a small nematic correlation length. So the norm is almost one. So in the previous energy, essentially, this term wants to either is not there, or this is large, so this has to be very small. The norm has to be almost. This is the idea. And so the result essentially is that, say, for instance, in the unit ball, the minimizer for this energy are smooth, and in the case where there is no norm constraint, so this case, essentially, indeed, there is no uniaxial phase. So we don't have any zero. Okay, and moreover, for the biaxial surfaces, on the ball with this homeotropic boundary condition, essentially we do have all the possible values of the biaxiality. At the boundary, the biaxiality is precisely 1, because the boundary condition is positively uniaxial. But indeed, for topological reason, there has to be also negative uniaxiality inside, and indeed all the possible values of the biaxiality are attained, even with the non-trivial topology of the biaxial surfaces. So in a sense, the boundary condition carries some topology that is propagated inside and is reflected in all the level set of the biaxiality. This is the idea. And as a corollary, there is an equilibrium, a critical point in both cases, which is purely uniaxial, and is a kind of radial extension of the boundary value. Okay, and this is the unique uniaxial critical point, thanks to an old result by Xavier. Yeah. And essentially, this critical point turns out to be not minimizing and not even stable energetically. Okay, and the ingredient, I mean, possibly the interesting issue is really this non-trivial topology, which is connected with the title of my talk, Torus-like solution. What is the idea is that now I'm giving you in the next slide the conjectural picture of this family of biaxial surfaces. So what is next here in this picture is exactly the image you should have in mind. So in the unit ball, in the domain, what you have is a foliation by the level sets of the sign biaxiality with a family of concentric tori. Okay. This picture is done for the opt vibration from S3 to S2, where you open up S3 to R3 by conformal stereographic projection, if you want. And essentially, this explicit map is valued in C times R, but actually in S2. And if you cut S2 by horizontal plane, you take horizontal circle and you take the preimage. The preimage of each horizontal circle is a torus. As you vary the circle in S2 and you take the preimage, you have a family of concentric tori. Okay? And essentially, the conjectural picture for Landau-De Gennes is exactly that. That you have this family of level sets for the sign biaxiality of the minimizer, in which the level set 1, biaxiality equal to 1, is the boundary of the ball, where the boundary condition is positively uniaxial, and the symmetry axis, where you should have a positive uniaxiality as well. While instead, the negative uniaxiality or in the common soul of all these tori, okay, which is an horizontal cell. And indeed, the conjectural picture is exactly this one. This is, in a sense, another way of looking at Q tensor. Instead of taking graph of the level set of the biaxiality. Here, what you are doing, you are kind of plotting this family of tensor. At each point, the tensor gives a quadratic form. The unit ball of the quadratic form is a kind of ellipsoid, so you have a family of ellipsoid. So you are describing a family of ellipsoid, and essentially the conjectural picture for the minimizer is something that is positively uniaxial on the boundary and on the symmetry axis, conjectural symmetry axis, and is negatively uniaxial on an horizontal circle. Here you are slicing the ball by a vertical plane. And the red line is rotated into a torus in which the sign biaxiality is 0. That is essentially here on this torus, essentially what you have two opposite eigenvalues and a 0 eigenvalue in the middle. So in a sense, it's the surface where the three eigenvalues are as far as possible. Okay? It's the maximal biaxiality. So this is the conjectural picture that one would expect. I'll be back to that later. So far, what we have is just a weaker result, namely that we have some non-trivial topology, but we don't know exactly that the genus of this surface is 1 as for the dome. So it's a kind of weak signal. And just briefly, the idea or the proof is a mixture of analysis and topology. Analysis for the regularity theory of harmonic maps is essentially used in a perturbative version, and there is some topology in the end. So essentially, one has a monotonicity formula to say that the energy on bolts divided by the radius is monotone. This allows to essentially rescale the mapping to analyze the small scale behavior, blow up, having the compactness of the blow up. Then there is a Lewis property identifying the limiting map under blow up, showing that there is a conical structure, essentially scaling invariant. And then by passing minimality, in particular stability to the limit, one has a vanishing for the possible limits. So once the limit under blow up is constant, essentially it means that the scaled energy at small scale is very small. And then one can analyze the BMO norm, and in terms of it showing that the oscillation decays in a quantitative power-like decay, so that one has a continuity through Campanado spaces. And once there is continuity, essentially there is another iteration in the spirit of De Giorgi due to Dirichlet that shows that the gradient is bounded, and then the equation essentially linearizes, and one has higher regularity, even analytic regularity by the older from Nirenberger, Morey, and Friedman in the 50s. And it's funny that this analytic regularity is crucial in our result, in the sense that then it allows to use some argument which is truly valid in the analytic category, not in the infinity category. The Loyasiewicz reduction theorem in particular, which in a sense allows us to say that the regular level set are smooth surfaces, and by an argument using the Euler class, for oriented vector bundle, we show that this surface has positive genus. But then we can pass from a regular level set to singular level set because of analytic regularity, keeping the topological non-triviality. Because the singular level, for instance, beta equal -1, is a strong deformation retract of the regular level. So non-triviality of the regular level reflects in non-triviality of the singular level. So this is the situation, the result we had in the general case. And now to have more insight and to go in the direction of the conjectural picture I presented here, I go in a symmetric setting. So this picture is evident that it has an S1 symmetry, and now I'm playing with that symmetry. So in the next slide, what I'm going to do is to use this axial symmetry. So I'm taking S1, and I act both on the domain by rotation around the vertical axis, working on the axisymmetric domains, and on the image on tensors by acting on tensor by conjugation. And essentially this way, I can consider the 5-dimensional space of a symmetric matrices with zero trace and decompose into invariant subspaces with respect to this S1 action. And essentially I have a diagonal part which is L0, which is invariant, fully invariant by the S1 action, and one which is this block here, which is which has a degree 1 rotation acting, and L2, which is you see 2 rotation is a kind of degree 2 action. So this way, in a sense, you can identify the space of matrices with R plus C, and you have a graded action of S1, and this will be very useful because it allows to use some complex geometry to play with them. So essentially, out of that, you can play in the class.
This is a nonsense. Like an ansatz of looking for solutions.
Yeah, exactly. In a sense, exactly. To simplify things, you make an ansatz, you restrict to a class of S1 equivariant maps so that everything is simpler, in a sense. In particular, you can minimize the energy in this class of maps and show that the critical points are truly critical points for the functional solution for the equation. In particular, this allows to say that, in a sense, for the regularity, what happens is that instead of working, say, on a unit ball, you are working on an half disk which is rotating by invariance, and so you are reducing, in a sense, to a 2-dimensional problem, but on a domain with as a boundary which is partly singular, so that in a sense regularity out of the symmetry axis is for free, but on the symmetry axis there are subtle issues that one has to analyze. We will see. So there is still a reduction and simplification. And so essentially the idea is that in this class of symmetric maps we have minimizer, and minimizer are smooth away from a set of the symmetry axis which is either empty or finite. And essentially we can say also what is the behavior at these isolated singularities. That is, when you rescale around the point on the symmetry axis, we see all the same conical profile. And this conical profile I described by extending homogeneously a map from S2 to S4, which has this particular form. It's inside R plus C, the map. You see 0 on the last entry. So essentially, you are plugging in S2 inside S2. It's an equatorial embedding of S2 inside S4, possibly with a phase rotation. So essentially, it's just an isometry to plug in S2 inside S4 equatorially, possibly with a rotation. And the idea is that this classification requires some complex geometry, because the profile you have a priori are harmonic maps from S2 into S4, and it's possible to lift them to CP3, which is the twistor space of S4. There is a so-called Calabi construction of a lift. I don't want to explain too much this issue. Essentially, these are complex lines inside C4. C4 is like the quaternionic plane, H time H. H are the quaternion. Essentially, this map is the twistor vibration is sending a complex line inside its quaternionic envelope. And the quaternionic line inside the quaternionic plane are exactly S4, are exactly the real quaternionic line. So essentially, this map is completely natural. This map is useful, is an isometry, is a Riemannian submersion, and essentially the idea is that these maps that appears as possible profile can be always lifted, and if this is harmonic, then this is holomorphic and is also horizontal with respect to this vibration. So in a sense, you have a lot of information. It's holomorphic, this map, so you can use some holomorphic method, in particular being holomorphic between algebraic variety is algebraic, so it's given by polynomial map, and essentially since you have rotation on the domain, rotation on the image, and you can put the rotation and S1 action also here, essentially you can classify the lift. So the lift are explicit. The idea is the lift are explicit, are polynomial, and contains two parameters. So these lifting are an explicit family of degree polynomial. And once you play with an energy minimality, you can say even which are these values of the parameter. So in a sense, out of that, you really get that these are the possible maps. So this is a partial regularity result using some complex geometry. This is the issue. And now what I want to do, so this is say a partial regularity theory with a profile, a unique limit using Loyazievich, Simon Loyazievich inequality to show uniqueness of the tangent cone and the isolated singularity. So it's a kind of qualitative picture. But now what I'm going to do in the next slides is just to show that playing either with the boundary condition or with the shape of the domain, I can make either this singular set to be empty or to be non-empty. I can play with the domain of the boundary condition to see exactly the two opposite situations. Okay, and the idea is that one possible thing is that instead of using the normal field to cook up the boundary condition, now I tilt the boundary, the outer normal, being vertical on a large part of the boundary, pointing upward or downward, and making an alpha tour in a small portion of the boundary. Okay? So the idea is that I can create a family of boundary conditions in terms of family of vector field, which are a deformation of the outer normal field. And if I do this deformation in smaller and smaller region, essentially there is some energy concentration happening in a smaller and smaller region, with the boundary condition always carrying a non-trivial topology, because if I follow a small contour, an S1 in the domain, and I see what are the corresponding tensor, I see always the non-trivial element in the fundamental group. So in a sense, these boundary data always have a topological charge. And in the limit on delta, when I collapse this region, essentially I do have boundary data which are bounded sequence in the fractional topology space, but that are collapsing to a map. You see the limit is a constant, because you see in all the region this constant vector either upward or downward. So it's the same map, the constant map, because n minus n are indistinguishable. So in a sense, as a boundary condition, we are weakly converging to a constant map, but there is some topology which is escaping, and it's escaping on the horizontal circle, which is the limit of this purple region. So there is some topological concentration effect which is happening, and there is some energy collapsing there. And the point is that since essentially we are getting a boundary data which are almost constant everywhere, the regularity, the constancy of the boundary condition propagates near the symmetric axis in an almost constant minimizer, so in particular in a regular minimizer. So the idea is that for delta very small, the minimizer are smooth, and essentially we have this conjectural picture that the green region where the sign biaxiality is negative becomes a solid torus, okay, or a finite union for solid. And we can do something similar, but in the opposite. We can perturb the radial anchoring, the standard boundary condition, using this family that I presented before of harmonic spheres. Now, instead of having an S1 element for mu1 and 0 on the second, I take delta small here. So I almost have the profile at the point singularities, but it's slightly perturbed. And using this boundary condition on the ball, essentially the effect is that for minimizer, we do have non-empty singular set. So for this deformation of the radial anchoring, singularity do appear. And the mechanism in a sense is that when delta is going to 0, there are pairs of singularities. Some of them stays inside the domain, and others are ejected to the boundary. Because of the fact that under this convergence, there is some energy concentrating at the point of the boundary. So there is a bubbling of an harmonic sphere for the boundary data occurring at this point. And since the data are concentrating energy here, this allows a singularity to escape towards the boundary. Okay, this is the kind of mechanism behind that. And okay, in particular, the level set of the biaxiality this time are not tori, but there are spheres with poles at the opposite singularities. There is a natural +1 or -1 that you can put to each singular point. So spheres are connecting these opposite singularities. Okay, so there are kind of spheres that are making connections. And okay, so this is nice and it's consistent with the numerics, where you see essentially using the classical biaxiality, which is connected to our sign biaxiality this way. Numerics shows different equilibria. You see color and you see arrow here, and the blue region is where you have essentially beta equal 1, yeah, exactly. So our sign biaxiality is +1 essentially, so that beta is equal to 0 is the blue region where you have positive uniaxiality. Instead, the red region is where you have essentially the sign biaxiality equal to 0. Okay, so this is the location that you have for the uniaxial critical point, the unstable one. This is for the torus solution, where you have a negative biaxiality, and in particular negative uniaxiality making a solid torus. And here you see the section of the spheres that I was talking about just before in the numerics. And these are the typical names in the physical literature for this sort of equilibrium. And so in a sense, what we did, this is the conjectural picture when the boundary condition is really the radial anchoring. What we did is for perturbed boundary data to construct both the ring discrimination solution and the split core solution. This is the idea, what we are doing. So it's coherent with the numerical evidence, in a sense. And of course, the big open problem is to show that for this true boundary condition, indeed, the minimizer is smooth, and in the whole class without, sorry, when we minimize in the symmetric class, we don't want to see singularities. We want to say that for this boundary condition, the minimizer is smooth. And on the other hand, if we minimize in the non-symmetric class, where we know that there is smoothness, we would like to infer symmetry. So in a sense, if you assume symmetry, that singularity that you would like to rule out. Otherwise, if you don't assume symmetry, then you know smoothness of minimizer, but you would like to infer symmetry. So on both approaches, there are big open problems either the symmetry or the smoothness. Okay, this is the issue. When this is the boundary datum. What we did is for perturbed boundary datum show that both the two situations are possible. This to put in a comprehensible scenario our results. So now what I'm doing next is to play instead with the domain. Instead of perturbing the boundary condition, now I'm going to keep the boundary condition in terms of the outer normal, but I deform the domain. Okay? So what you see next is the deformation of the domain. And essentially, so what I'm doing here, I'm perturbing the ball inside as a family of cylinder, and depending on the ratio aspect of the cylinder, either is very large or is very thin and long. There are opposite situations happening. For you see a very large cylinder, L1 is much bigger than L2, so it's very large. It's kind of punctured. Then the minimizer are smooth and of torus type. When as opposite, say L1 is fixed, but L2 becomes very long, so the cylinder is very elongated in the vertical direction, then the minimizer must have singularities. So you have a kind of split minimizer, okay? And in particular, when you minimize not in the symmetric class, the minimizer are smooth as a consequence of the first theorem I presented. But what happens is that the minimizer cannot be axially symmetric because the axially symmetric minimizer must be singular. So there is a symmetry breaking result. And this is coherent with numerics again, because what the people in numerics did is exactly on a cylinder, minimize the energy, and see that for minimizer, the axial symmetry is broken, and torus appears, but they are vertical. So essentially, the S1 symmetry is broken. Of course, the boundary condition and the domain do have O2 equivariance. So what survives is the Z2 symmetry of reflection with respect to a vertical plane. This survives, but the S1 symmetry is broken. Okay. And just to conclude, a few words about future direction. One thing is to construct critical points with prescribed singularities, which is kind of in the spirit of results for harmonic maps, also in the context of Cartesian currents. The idea is that one can modify the energy, taking a relaxed version of the energy, in such way, in a sense, to penalize or possibly prescribe the position of the singularities. And this is challenging. It's not clear if we can do that. And there are also other interesting directions in which we change the boundary condition. Instead of taking a radial boundary condition, we take tangential boundary condition, or with prescribed angle. And this is coherent with the Gisborne-Landau model, where, in a sense, you can have boundary vortices because you have a certain winding degree at the boundary trace. And in this case, you should imagine that the biaxial surfaces are kind of surfaces that touch the boundary of the domain. And the negative uniaxiality should be kind of lines, but which are not a circle sitting inside the domain, but are open arcs arriving at the boundary singularities of the boundary condition. And of course, also the dynamics is interesting. The first thing to try is the L2 gradient flow for the Landaude Gennes energy, but with this norm constraint, this U of constraint on the norm, which makes the problem highly nonlinear. It's similar to the harmonic heat flow for the L2 flow for the Dirichlet energy for maps into here. with an extra potential term in the energy. So of course, constructing weak solutions should be doable, but the main issue is to prove, in analogy with those papers, finite time blow up. This is much more subtle. And essentially, there are recent papers on the harmonic heat flow where, in certain symmetric situation, you create blow up at a certain time at prescribed location, because you can use gluing methods as in the spirit of the talk yesterday, to essentially construct a model solution with prescribed blow-up profile, in a sense. It's interesting to understand it when there's something similar also here. And of course, the true dynamics is the very settler system. So in that case, you don't have just the tensor, but the liquid crystal also moves as a fluid. So there is a coupling between the Navier-Stokes equation for the fluid motion and the L2 gradient flow for the Q tensor, and also deterministic and stochastic with the stochastic forcing, trying to understand if this is compatible with the norm constraint, which is highly non-obvious, and it's key to be understood. Okay. Maybe I'll stop here.